So growing space, meaning also growing hypothesis space. So if we have more features, of course, the hypothesis space grows. The lower the hypothesis space is, the easier it is to find the correct hypothesis. I think that's quite intuitive. And of course, also the less examples you need to properly test a hypothesis. I mean, just think about some linear dependency, maybe. Yeah? So in 2 dimensions, you need 2 points to actually define a line, which is a linear dependency. Yeah. So in a 3-dimensional case, in a 3-dimensional space, a linear dependency among everything is a hyperplane, a 2-dimensional plane, and you need again 3 points to actually span that, and so on and so on. So in a 50-dimensional case, you need 50 points in order to span, or 50 plus 1 even, to span a 49-dimensional hyperplane. Yeah? So that is the idea of growing hypothesis space. You need more examples to actually define or test hypothesis, yeah? Prove hypothesis, define models, and so on and so on. Yeah? So that is meant by growing hypothesis space. Yeah, so consider F a unit multivariate normal distribution and a normal kernel, KDE. Yeah, so the aim is to find an estimate F hat here of F at the point 0. Yeah, and we'll see that the relative mean square error should be fairly small, of course. For example, we want to have something like the expected difference between the estimated or the estimation at 0, at point 0, and the estimation or the true point, actually the true value at point 0 times the squared value at point 0 should be less than 10%, for example. Yeah, so we want to have a fairly small mean square error of our estimate. And if we try to somehow estimate that, we'll see that with growing dimensions, we need much more samples to achieve this this error rate, actually, this 10% error rate. Yeah? So in 1 dimension, we need just 4 samples in order to get an accurate estimate. For 10 dimensions, it's already almost 1 million. Yeah? So, so that is much more than exponential, or that's kind of exponential relationship, which means that for a fairly simple thing, if the dimensionality grows, we the number of estimates, the number of observations we need in order to be sure that some model actually fits or holds or whatever grows dramatically. So that is also illustration of the growing hypothesis space here. Yeah, and then this point of these empty spaces and empty tails. So first of all, empty spaces. So, well, if you consider a d-dimensional space with partitions of constant size 1 times m, for example, here. Yeah, so here, for example, we have a 1-dimensional data space, and we want to have, say, 4 cells. Yeah, so we have 1, 2, 3, 4 partitions. Yeah, so now if we increase d, the number of cells also increases, and it even increases exponentially. So you see here that in 2 dimensions, we already have, for n equals 4, we have, well, 4 partitions in each dimensions, meaning that we have 16 partitions overall. Yeah? And in 3 dimensions, we already have 46 partitions, 3-dimensional partitions, yeah? And so on and so on and so on. Yeah? So now suppose we have x points, say 10 points, randomly placed in this space here. In low-dimensional spaces, of course, there are very, very few empty partitions, because many points just are somewhere in one of these partitions. Yeah, so most of the partitions have actually many points in it. Yeah, but if we have the same number of points, say 10 points here, spread randomly over this data space, in this data space, we see that here we have, well, if it's randomly, we have 2 times 2.5 observations per partitions, at least that's what we expect here. Yeah, 10 times 4. Here we have 10 times 64. So most of the or many of the partitions of the grid cells here will be empty actually. Yeah? So in high dimensional spaces there are 4 more partitions than points. So many of these partitions will be empty. That's just what you have to keep in mind. Yeah? Meaning that a lot of, so if we have the same number of points in a small space, like a one-dimensional space, and a larger space, like a three-dimensional space, we have to be clear that there will be a lot of partitions, meaning a lot of part, a big part of the data space is just empty. There's nothing in. Yeah? There are no points in there, no observations. Yeah, so analogously, like this one here, so consider a simple partition scheme which splits the data in each dimensions into 2 halves, not into n or 4 halves, but just into 2 halves. For d dimensions, we obtain 2 to the power of d partitions. And now just a little bit math. So if we consider 10 to the power of 6 samples in the space, 1 million samples here, for d smaller than 10, such a partition may make sense, yeah, but for 100 dimensions there are around 10 to the power of 30 partitions, but we only have 10 to the power of 6 points. So most of the partitions we have for d dimension for 100 dimensions will be absolutely empty, obviously. Yeah. So just keep that in mind. That is simple math, which just illustrates what has been done here more abstractly. So this is most of the space will be empty. Yeah, once again, empty spaces entail. So the data space is empty. We just talked about it, and very, very surprisingly, it's basically the center which is empty. We'll see that points in high-dimensional spaces tend to be placed at the borders of the data space and not in the center. Looks a little strange or sounds a little strange, but that's also very, very simple math. So consider a hypercube range query with side length s, yeah, in all dimensions, placed arbitrarily here in the data space. Yeah, the data space is normalized between 0 and 1. It's d-dimensional, yeah, d-dimensional, and we have a window query of side length s. Yeah, it's just a hypercube here of side length s. And E is the event that an arbitrary point lies within this blue shaded area, within this hypercube here, hypercube range query with side length s. Yeah? And the probability for this event actually is s to the power of d. Yeah? So with increasing dimensionality, even very large hypercube range queries are not likely to contain any point here. Yeah? So you see here that it's just going down here. Yeah? So for 80 dimensions, even for a very, very big hypercube, yeah, so the green one here, the probability is more or less 0. Yeah? Meaning that in high dimensional spaces, all of the points are outside of the blue one here. It's somehow counterintuitive. But if you actually think about it, it's very, very clear, because yeah, if you just say, okay, what is the volume of this in between here and the volume up here? Yeah, in smaller dimensions, the volume in the middle here of this blue shaded area is probably much larger, especially if you take something like 0.9, than the one that is outside here. But if you increase the dimensionality, the volume outside here grows much faster than the volume of this one inside here. Yeah? And that is why the probability for the event decreases dramatically. Yeah? And that shows us that most of the points in high dimensional spaces will be just at the borders of the data space. Yeah? Because that is where actually most of the area of the data space is. Sounds totally weird, but that's how it is. Yeah?